This is it. 16-9. Last lesson of the year, the decade, the semester, the course, the chapter. High school mathematics. Could be last math lesson forever, right?
Forever.
You might not have. It depends on your major.
No, I got over that. I don't know. You can scribble all over my notes if you want to bother me.
That is.
You want to do it? Go ahead. Wow.
All right. So, we write Green's theorem in a vector version. So the line integral of f dot n ds. So yesterday we learned curl f dot n, done as the double integral over the area of the projected region. So anyway, divergence theorem. So this f dot n is actually the divergence of f over the area of the region, where C is the positively oriented boundary curve of the plane. If we are seeking to extend this theorem to vector fields, we might guess that this is in 2 dimensions, that in 3 dimensions, that f dot n ds over the surface would be the same as the divergence xyz over the volume, the triple integral that gives the volume. So we've established that the line integral f dot n can be computed as the divergence over the area. Now we've got that the surface integral f dot n can be equated to the triple integral over the volume of the divergence. And so that's a guess. Is it true? Yes, it is. Okay, so here's what you actually have to write down. So this is, so that was a lead in. So the boundary of E is a closed surface, and we use the convention that positive orientation is outward, that is, the unit normal vector is directed outward from the surface. Let E be a simple solid region and S be the boundary surface of E. Given with positive or outward orientation, let F be a vector field whose component functions have continuous partial derivatives on an open region that contains E. Then the surface integral of f dot ds is equal to the triple integral over the region E, the surface E, of the divergence of F with respect to the volume. Thus, the divergence theorem states that under the given conditions, the flux of F across the boundary surface of E is equal to the triple integral of the divergence of F over E. Divergence is the dot product of the partials with the matrix, or with the vector, with XYZ, with your vector components. So it's really like if you take the gradient and just add the components together, essentially. All right, so that's your divergence theorem. Was it Ketke, Johnson, and there's one other one. Oh, Fogarty. So, yeah.
You should try one.
Okay.
Still frozen.
How do I go? Come on.
It's frozen.
Oh, it's frozen. There we go. Okay. All right, so find the flux of the vector field f of x, y, z equals z, comma, y, comma, x over the unit sphere x squared plus y squared plus z squared equals 1. So there's an easy way to do this, and there's a slightly harder way to do this. We're going to do this the slightly harder way. And then I will show you the easier way. All right. So first thing I want you to do is find the divergence of f. So take a moment and see if you can find the divergence. Yeah, so divergence is, so you have d dx, d dy, d dz, dot product with the xy, how do I say this, like the x component. I don't want to say xy because it's not xyz, but like your components of f, right? Whatever they are. Right, so you're doing partial x on the first component, partial y on the second component, partial z on the third, and adding them together.
Oh, editing.
Yes, this is a dot product. Right, dot product, you add them. So cross product, you end with a vector. Dot product, you end with a scalar. It is one.
Okay.
Yep. Is that okay? Oh, I'm sorry. You go here. I'll cover it up.
Thank you.
All right, did you get one?
Yeah.
Yeah. All right. Is that okay? Are you really lost?
Yeah.
So it's partial x on your first component, right? Plus partial y on the middle, plus partial z on the left.
It's not partial of the unit.
No. It says we're doing the divergence of f. This is f, right? Don't rip it out. Just start again. We're not that far in. You can just cross out what you've done. I've never had a class with this much discussion about note taking. Like, it's very, no. You don't. It's just a matter of being able to move on after something is wrong. Yeah. Kajesh, can you go back to your desk, please? Because you tend to be distracted a little bit over there. Yes. Okay. You got one? Good. All right. So now we're going to set up a triple integral that calculates the volume of the sphere. What would be the easiest coordinate system to use? Spherical. Spherical. Let's do it. It's been a while since we've done a spherical triple integral. So let's go ahead and set up a triple integral that would give us the volume of this sphere. So think d rho dp d theta. Okay, well, what does theta have to go from? 0 to 2 pi, right? Okay. Phi, remember, is going to be here to here, so it's going to be 0 to pi, right? And then rho is the radius of your sphere, so 0 to 1. Easy peasy. But you have an integrand. It's just rho squared times sine phi. Yes.
I don't know why I'm
Yeah. So the divergence, it's the divergence that is your integrand, but since the divergence is 1, it's just 1, right? So you end up with just the triple integral of rho squared sine phi. Now, okay, let's go ahead and evaluate. Take a minute and evaluate the integral. If you did it correctly, you should have gotten 4/3 pi, right? Well, let's just think about how we could have made our lives easier. Since the divergence was a constant, right? So if we have the divergence and it's a constant and it just goes out front, what does this triple integral give you? It's just the volume of a sphere with radius 1, right? You could have just done 1 times 4/3 pi. Ah. But see, then we wouldn't have had the fun of reviewing spherical, right? So.
Is that fun though?
Okay. All right. We all good? Good. All right. One more. So we're going to use, actually there's a couple more things. So use the divergence theorem to calculate the surface integral of f dot ds, that is, calculate the flux of f across s if your f is 3xy squared xe to the z cubed, and s is the surface of the solid bounded by the cylinder and the planes x equals -1 and x equals 3. So you have a cylinder that is kind of like in the YZ kind of realm, right? So it's kind of a sideways cylinder from x equals -1 to x equals 3. So it's actually like your regular cylinder that looks like a can, right? With x boundaries. And so you really want to think about projecting, like doing, like, well, I guess how do I say this? When you do your volume, I would do my volume in cylindrical coordinates, but I would do it thinking of it more YZ and not XY. I don't know if that makes sense. So anyway, or you could just do it in rectangular coordinates, but I did it, I'm pretty sure I did this in cylindrical. Sideways cylindrical. So, here's, okay, let me explain this better. If we're going to do cylindrical coordinates normally, normally with cylindrical, you have an R and you have a theta and you have Z, right? So you have R theta Z. Now, instead of R theta Z, you would have R theta X. Your X kind of becomes your Z. Okay. Here's somewhere too. No, I don't. Okay. So the question, I'm going to move this down. So we're all good on divergence, right? Okay, so let's just move this over for a minute. So what we have in the XYZ plane is, instead of having the cylinder oriented where it's kind of revolving about the Z-axis, we're revolving about the X-axis. So it kind of looks, I can't draw 3D. Okay, oh, I got it. I have an idea of how to do it. Okay, so if I put a circle here and a circle here, that didn't look good. There's my cylinder. That's not bad, right? Thank you. Okay, so anyway, so this boundary is x equals whatever it is, 3. And this boundary back here where it intersects the x-axis is at -1. It's really awful. Okay, so anyway, so that's what we got. So really what you're doing is kind of like your x becomes your z, your y becomes your x, and your z becomes your y. You're doing the exact same thing you've always done, just changing the letters.
Oh, I'm just asking about the integrand.
Oh, okay. Oh, the integrand? Okay, so what we had in rectangular, so I'll show you rectangular and then we'll convert to cylindrical and then we'll move on. All right. It's so pretty. But you know what? We're going to sound awesome when we sing our calculus carols.
Oh, yeah. We should go into choir and sing. We should go into choir and sing. That would be so awesome.
Okay, so in rectangular, when you have the equation, y squared plus z squared equals 9. So think of it like solve for z plus or minus square root of 9 minus y squared, right? So think like this is your z, so you have like positive root 9 minus x squared, or y squared, negative root 9 minus y squared. So negative root 9 minus y squared to positive root 9 minus y squared. Your y's go from negative 3 to 3. Believe it or not, it's like they're all, anyway, negative 3 to 3. Okay. All right. So this would be the setup in rectangular. The issue with this triple integral is it's kind of hard to evaluate by hand, right? So if we want to convert this to cylindrical, we need to go to an r theta, but normally it'd be r theta z, but now we're going to be r theta x, because x is like the axis that our cylinder's kind of spinning around. All right, so how do we do that? Move this over smart. Okay, so how do we convert this to cylindrical? So your x is still going negative 1 to 3, but now we need an r and a theta that produces this circle, right? Well, your theta is still 0 to 2 pi, and your r is still 0 to 3. But your this right here, so this is the same as 3 times y squared plus z squared. Well, normally we'd have x squared plus y squared equals r squared, but now we have y squared plus z squared equals r squared because it's in the yz plane instead of the xy plane. Does that kind of make sense? So this becomes your r squared. Because we're in yz mode instead of xy mode. So, because y squared plus, how about this? Because y squared plus z squared equals 9, right? That's your boundary, right? Y squared plus z squared is the same as r squared. Okay, so you'd have 3r squared times r d theta dx. You could put x anywhere. It could be b anywhere. It's constant. Yeah, on the board, I had converted y squared to r cosine theta, or y to r cosine theta and z to r sine theta. But it doesn't matter because once you square, the cosine square plus sine square go to 1, and you're just left with the r squared.
And there's no reason you did x, like, normally z you would put
First, yeah, I know. I had x at the end here, so I just kept it. But you're right. You could put the x first. It doesn't matter because it's constant limits anyway, so that's fine. All right. So let's bring the problem back. All right. So this is me like converting it all like, kind of by hand to get to here. So after all is said and done, somehow get to here. 3r squared, and here I did dx dr d theta. So I don't know. Anyway. Yeah, and then you just integrate. Do you guys need a minute? Have you tried to integrate already? All right, I'm going to pause the recording, give you time. Where'd the recording go? It's in here. Pause.
Just surprised. How about one person from every table gets it right? The entire class gets it right.
Let's finish this problem.
Yeah, that's pretty
So,
Okay.
I got 486 pi. What'd you get?
I got 1.3 times 3 times pi over 2. 2 times pi over 2.
Is that equivalent? You got 243 times 3
Times pi over 2.
over 2. So you got 3 halves.
729 divided plus
81 times 3. Wait, I did. It's 243. But I did write that.
Wait,
975
wait. You got the same thing? Okay. Good job. You did it. All right. Good. Are there questions?
I have many
About this problem?
Oh, no, like,
All right, we did a spherical. We've done a cylindrical. Where's the where things go? Oh, that's right. It's in the computer now. Okay. So, an application of the divergence theorem occurs in fluid flow. We kind of talked about this yesterday with an application of Stokes' theorem, right? So let V be the velocity field of a fluid with a constant density rho. Then F equals rho V is the rate of flow per unit area. So if P sub 0 is a point in the fluid, then the divergence of F at that point is the net rate of outward flux per unit volume at that point. This is the reason for the name divergence. I don't know. I don't know enough to know why that means something. But anyway, there you go. Okay. No. All right. But you do need to know this, and like these next couple problems are actually kind of fun. All right. So this part is going to be in your homework. You're going to like it. I promise. Okay. Giving you my word. All right. If the divergence is positive, the net flow is outward near P, and P is called a source. If the divergence is negative, then the net flow is inward near P, and P is called a sink. I love that some of you are nodding. That really makes me feel good because this is all, I'm just reading this with, there's no real correlation going on in my brain. I can't make a connection. But that's okay. But I like doing the problems that they're going to ask you, so they're really easy.
Are they word problems?
No.
They're just going to ask
They're
if it's
picture
a
problems.
sink or switch.
Yes, you get pictures. You don't have to draw anything. Pictures are given. All right, so outward net flow, point is called a source. Inward net flow, point is called a sink. You ready to do a problem?
Sure.
No.
Yeah.
The first one I just show you how to, you don't have to do anything.
Let's do it.
Okay. Oh, whoa. Yo. How you doing, Laura? Me too. Really tired. Like beyond. I'm literally just telling myself each moment, like how much time is left. You can do this. You can do
I
this.
focus on how many slides there are in the presentation.
Oh, I'm not just talking about this class. I'm talking about this week.
Yeah.
Oh, goodness. Yeah. Yep.
Okay.
Yes.
Like 100%.
Yeah. I thought last week was long, but now I realize I was mistaken.
Yeah.
This week is longer. Yeah.
These past like 3 weeks have felt like a year.
Yes. Yes, they have. Really, yeah. Yep. Okay. Are we good? Jack, are you done? Okay, here we go. Source and sink. All right. So we have a vector field given. And there are 2 points indicated on the vector field. So this one is not asking you anything. It's just explaining it so you can get the idea. This is why I'm telling you you're going to like this. Here we go. So for the vector field below, it appears, I'm going to make this bigger. For the vector field below, it appears that the vectors that end near P1, end near P1 mean they're kind of pointing towards P1. The vectors that end near P1 are shorter than the vectors that start near P1, meaning the ones that are going in are kind of shorter than the ones coming out. Thus, the net flow is outward near P1, so the divergence would be positive there, and P1 would be a source. At P2, the vectors that end towards P2 are longer than the vectors that are leaving P2, and therefore the net flow would be inward, the divergence would be negative, and P2 would be a sink. Okay?
Oh, that's it.
That's it.
What?
Okay? So, now, wait, now, okay, so this vector field was given. This is the vector field x squared plus y squared. So using the formula to confirm this, so if you actually find the divergence 2x plus 2y, you find your critical number, right, set this equal to 0, you end up with a y equals negative x kind of a thing as kind of your dividing line. And then something happens when you're above and something happens when you're below. So this is positive when y is greater than negative x. So the points above the line y equals negative x are sources, and the points below the line y equals negative x are sinks. Okay. All right. Are you ready to try one?
Sure.
Okay, let's do it. So for the vector field to the right, determine if the net flow is outward or inward at each of the points. Then determine if the divergence is positive or negative at each of those points. All right, I give you like 30 seconds.
Yes.
Point 1, would you say that point 1 is a source or a sink?
Source.
I would say it is a source. Tell me to just why you thought it was a source.
Because the arrows on one side are bigger than the arrows.
Good answer. Good answer.
Because the arrows going into P1 are smaller than the arrows coming out of P1. Yeah, so we would call it a source, which means that the divergence would be positive at that point. What about at P2?
It's a sink.
It's a sink. Why is it a sink?
Because the arrows on the bottom. The arrows on the bottom are larger than charge, and the ones on the top of P2 are teeny tiny.
Yes, that is very good. Okay. Which
Great
means
analysis.
that since point 2 is a sink, the divergence there would be
Negative.
okay. And here endeth the lesson.